the CPU scheduling, and we'll see some of the algorithm related to CPU scheduling. Okay. So when we talked about the process, so in the process, what we have learned about its state, right? Different states. So if we have, let's say, a new state, then we have, let's say, ready state, then we have a running state, and we have terminated state, termination state. Okay. So we know that here we have a scheduler which will take the process from new state to the ready state, which is called long-term scheduler. From the ready state to the running state, we required a short-term scheduler, and we have a mid-term or middle-term scheduler, which is responsible for taking the decision at the, let's say, some process is in the waiting state, and this waiting state, it has been suspended. So it will go to the suspend state. So it is called suspended waiting. And when this suspended waiting will be resumed again, so that decision will be taken by the suspended, and how we can resume it, it will be taken by the medium term scheduler. So from the running state, any process can go to the ready state, right? Any process can go to the ready state. And from the running state, any process can go to the waiting state. So how it will go to the waiting state? If it required any IO, then it will go to the waiting state. And from the waiting state, again, once the IO has been finished, IO is finished, it will go to the ready state again. So from the ready state to the running state, who is taking the process? So we have a short-term scheduler whose responsibility is to choose any process which is there in the ready state, or you can say in a ready queue. So here we have a queue in which we have different processes. Let's say this is P1, this is P2, this is P3, this is P4, P5, P6, P7, P8. Let's say we have 8 number of processes. So which process will go and allocate the CPU, or which process will be allocated the CPU, will be decided by short-term scheduler. And this particular short-term scheduler scheduler is actually taking that particular decision. So the short-term scheduler will take the decision which particular process has to go from the ready state or from the ready queue to the CPU, or allocate the CPU. Now, as I told you, here we have another term which is called dispatcher. Now what dispatcher will do? Short term will make the decision on which process will go to the CPU. Dispatcher will actually do the do the state of change of state. So how the change of state will be done from the ready to running? It is done by the dispatcher. So short-term scheduler will find out the process, and dispatcher will actually do the state change of that particular process from ready queue to running queue, or sorry, from ready state to the running state. Also, if some new priority process has been reached to the, let's say this is a process P9, if we are using some priority based scheduling, so if new priority process has reached to the ready state, then whatever is in running, it will find out the priority of that. If the priority of the running process is less than what is waiting in the ready queue, so dispatcher will again take the process from the running state and it will take to the ready state. So dispatcher is actually responsible for taking that process from ready to running and from running to ready. Okay. And short-term scheduler is responsible for picking up which particular process, or short-term scheduler will make the decision on which particular process will go to the running state from the ready state. So that thing means the taking the process from ready state to running state, or from running state to ready state, that is called context switching. Okay. Context switching means the context means the process control block related to the process will be changed, and again the program counter, everything will be changed, and the state will be saved for a particular process, and that whole process is called context switching. Means to provide the state, or to change the state of one process to another process, or you can say that to taking from the CPU, if we are taking the process from the CPU to the RAM, or from the RAM to the CPU, that is called context switching. So that process is called context switching, and who will do the context switching? Dispatcher will do the context switching. But who will give control to the dispatcher? So short-term scheduler will give control to the dispatcher. So short-term scheduler will decide that which particular process has to pick up from the ready queue and put it into the CPU. If a process in the CPU, it means it is running. So this is about the scheduling. So let's go to the slide. This is written: short-term scheduler select from among the processes in ready queue and allocate the CPU to one of them. So short-term scheduler is responsible for picking up any of the process, depend upon which type of algorithm we have used in the CPU scheduling. So based on that, it will pick up the process from the ready queue and it will give that particular process to the CPU, and dispatcher will actually do the state change, and in that way it has to save all the process control block, and it will take, or it will remove the process control block of the already running process. So that is the responsibility of dispatcher. Queue may be ordered in various ways. So this queue which we are talking about, that is called ready queue. Okay, that particular queue that we are talking about, it is called ready queue. Why we are using queue data structure here? So previously the queue data structure is based on how processes will reach to the RAM. So in that way the queue has been arranged. We know that what is queue? Queue is first in, first out, right? So whatever process is coming first will be getting out first. But there are some different type of queue. There may be the priority queue, in which we'll arrange the process based on some sort of priorities. Either the actual priority will be given, or there are some more parameter that will use as a priority. But basically, in a ready state, we have a data structure which is called queue, and that queue is called ready queue, because we have the processes here which are ready to run. So that's why it is called ready queue. Now the CPU scheduling decisions may take place when a process, so what are the different uh, conditions where the CPU scheduling decision will be taken place? So the first is switch from running to waiting state. So if something we are giving from running to waiting state, we need to do some sort of scheduling. If we are doing like running to ready state, then also we have to do some sort of scheduling. If we are switching the process from ready waiting to ready, then also we have to do some sort of scheduling. And when we are when a process is reaching to the terminated state. So here it says that under condition 1 and condition 4, the CPU scheduling which is done, it comes into the category of non-preemptive scheduling. What is the meaning of non-preemptive scheduling? So running to waiting state. If we are taking something from running to waiting state, or if something has been terminated, so that comes into the category of non-preemptive scheduling. And all other scheduling is called preemptive scheduling. So what is the meaning of preemptive and what is the meaning of non-preemptive? Let's try to understand these two. So scheduling, that is your CPU scheduling, has been categorized into two parts. One is called non-preemptive and another is called preemptive. Let's try to understand these two. What happened in non-preemptive? In the non-preemptive scheduling, when a process will go to the running state, it will not come back to the ready state. It means whatever the process burst time is, whatever the burst time of the process is, it will run all its burst time and then it will reach to the terminated state. So the transition will be from ready to running and running to terminate. This is the transition of non-preemptive scheduling. Means we cannot preempt it. We cannot halt that particular process to run. So whenever a process will reach to the running state, it will run its all the burst time, means it will run all its instructions and then it will get out from that particular running state and will be terminated. Now, what is the meaning of preemption? Preemption means if some process is running, is here, and in the running state, if something happen, right, based on the scheduling, let's say we are using some priority based scheduling. So what happened in some priority based scheduling is, let's say some new or a higher priority process comes into the ready state. So scheduler will have to allocate the CPU to that particular higher priority process. So whatever process which is running will stop the processing and will take that process to the ready state, and the higher priority process will put into the running state. If you are doing that, that is called preemptive scheduling. Another scenario is that if we are using some sort of round robin or will allocate that time quantum to each and every process. Let's say we allocate, let's say 2 milliseconds to each and every process. So what will happen? Let's say first P1 will go to the running state. It will run for 2 milliseconds. Maybe 2 milliseconds is not sufficient to run all its instruction. So P1 will go to the ready state, and there will be chance to P2, process 2, to come into the running state and will be allocated again 2 milliseconds. Maybe 2 milliseconds is enough for the process 2 to execute. Then it will execute its whole bus time and it will reach to the terminal state. Then again P3 will come 2 milliseconds. Then P4 will come 2 milliseconds. So if it is not finished, it will again go to the ready state. If it is finished, it will go to the terminal state. So every process will be allocated some time quantum that will be used in a round robin CPU scheduling. So when we'll see the round robin CPU scheduling, at that particular time, you'll see that how this preemption take place. So preemption means forcefully, if some process is running and forcefully we are deallocating the CPU from that particular process and we are putting that process into the ready state again, that type of scheduling comes under the category of preemptive scheduling. So I think you get it. So if forcefully we are deallocating the CPU from any process and putting that process into the ready state, then that type of scheduling comes under the category of preemptive scheduling. Non-preemptive scheduling means if any process will reach to the CPU, then it is going to run all its instruction and then it will come out from the CPU. That is in the category of non-preemptive scheduling. So I think you might have the clear picture right now in the CPU scheduling. So we have the two categories, non-preemptive and preemptive. Okay. Consider access to shared data. So what will happen is in the preemptive scheduling, these are the scenario. Let's say 2 or more processes are using the shared data. So might be one process is running and then that has been deallocated and put it back to the ready queue, and then again new process will come, and again if the shared data will be there, then again it has to be deallocated in that way. So if shared data comes into the picture, we have to do preemptive. First scenario. What is the second scenario is while kernel mode. So when we are moving from the user mode to the kernel mode, we have to forcefully deallocate that particular process. So some sort of interrupt occur into the system, or some sort of, let's say, system call has been generated by the operating system. So the process has to be deallocated. So this is also a way why we have to do preemption. Consider interrupt occur during crucial IO activity. So that is also comes into the picture. So if we have some sort of system call or some interrupt occur. So these are the additional scenario in which preemption will take place. What are the two scenario that I told you? First scenario was if some higher priority process comes into the picture, or there is a time quantum that has been finished for that particular, or the time quantum is done with this particular process, then another process will come into the CPU. So we have these 5 scenarios in which preemption will take place. So what happened into preemption? The process will go from the running state to the ready state, okay, or from waiting state to the ready state. So from the running it will go to the ready, or from the waiting it will go to the ready. In both the scenario, we have preemption that will be taking place. Now I told you about the dispatcher. What is dispatcher? So as I told you, the short-term scheduler, the responsibility of the short-term scheduler is to decide which particular process will be allocating the CPU. Now, it is the responsibility of the dispatcher to actually perform that thing. Means it will do context switching. It can change the switching to the user mode and jumping to the proper location of the user program to restart the program. It means the whole process of context switching, that is the process, let's say PI, which will be allocating the CPU, and there is another process PJ, which is deallocating the CPU. So that switching has been done by the dispatcher. Let's say here we have a RAM. RAM means your ready state. This is your running state. Dispatcher latency means time it takes for the dispatcher to stop one process and start another process is called dispatch latency. Means it will take some time, right? Means we are just stopping one process to execute. We are taking that process and putting into the ready queue. Another process we are taking and putting into the from the ready queue to running state. So that transition time is nothing but dispatch latency. So the mainly that latency is to save all context, means to save all process control block related to process, let's say PI, and to save all the process control block related to PJ. So these two is taking some time. That particular time is called dispatch latency. Okay, dispatch latency. So I think you understood three things. First, responsibility of short-term scheduler, responsibility of dispatcher, and what do you mean by CPU scheduling? We have two types of CPU scheduling, preemptive and non-preemptive CPU scheduling. Now let's see the scheduling criteria. Means whatever the algorithm we have related to CPU scheduling, to take some of the criteria in mind, we design the CPU scheduling algorithm. So what are the criteria we have? The first criteria is CPU utilization. Means we have to keep the CPU as busy as possible. That is the first responsibility of any scheduling algorithm. The second is throughput. Throughput means number of processes that complete their execution per time unit. It is called throughput. Throughput is also called efficiency. Efficiency of a system means how fast we are completing the execution of a process. So this is another parameter of CPU scheduling. So we take some sort of CPU scheduling which is giving us the good throughput, and there are some sort of CPU scheduling which is giving us less throughput. Now next is turnaround time. We know what do you mean by turnaround time, right? So the amount of time to execute a particular process means a process when it comes into the ready state, and a process when it will reach to the terminate state. That time duration is called turnaround time. Okay, and in between we have running, right? So a process is coming means the arrival time of a process and completion time of a process. So this is arrival time of the process and this is the completion time of the process. So turnaround time is completion time minus arrival time. Getting it? So once a process, when it is coming into the system and when it is going out of the system, that duration is called turnaround time. So the amount of time to execute a particular process. So the whole execution will take place. Now what is waiting time? Waiting time means amount of time a process has been waiting in ready queue. Means how much time duration a process is spending in the ready state or in the ready queue. That particular time is called waiting time. So here, whatever the time duration process is spending into the ready queue, it is called waiting time. And whatever the time a process is spending in running, means inside the CPU, is called burst time. So what you can say is turnaround time is also called waiting time plus burst time. So that is, you can say that is also a turnaround time. Response time, we know what do you mean by response time? When a process is a time when a process is getting its first CPU, then that particular time is called response time. So the amount of time it takes from when a request was submitted until the response is produced, not output, for time sharing environment. So until the first response is produced, means when the first time a process will be allocated the CPU, that particular time is called response time. It means, let's say a process has arrival time, which is 10 a.m. and process will be getting the CPU, first time CPU at 10:10. So what is the response time? Response time is 10:10. This is the response time. So the first CPU allocation is called response time for a particular process. So all these are different criteria in which, based on that only, we used to create the CPU scheduling algorithm. Now we have these algorithm has some optimization criteria also. So how we can say that which particular algorithm is optimal algorithm and which is giving us the good throughput, good maximum CPU utilization. So these are that. So what is our target? Our target is to maximize the CPU utilization. So we have to use those algorithms which is maximizing the CPU utilization. Second, the algorithm who is maximizing the throughput, means efficiency, means how much time in a particular time duration, how many process we have executed. That is called throughput. Minimize the turnaround time, means the whole execution time has to be minimized. This is another criteria for any scheduling algorithm. Then we have to reduce the waiting time also. We don't want that a process will wait for a longer period of time. So we need to minimize the waiting time. What is the next thing is we need to minimize the response time. So if a process is ready to run, so as soon as possible, we have to allocate the CPU to that particular process. So all these are the different optimization criteria. We have seen all those things here. That is the scheduling criteria. But these are the optimization criteria. Means the CPU utilization has to be maximized. The throughput has to be maximized. The turnaround time has to be minimized. The waiting time has to be minimized. And the response time also has to be minimized. Getting it? So all these are the criteria, and what we have to do with all those criteria is showing here. Now let's come to the first scheduling algorithm, which is called first come first serve scheduling algorithm. Okay. This is the first category of scheduling algorithm, which is called CPU scheduling algorithm. Now, what do you mean by first come, first serve? Means which process is coming first, we have to serve first. And which process is coming after that, we have to serve for that. So we have to use queue for that, right? In the queue, we have to put those process which is coming first. And then we have to put another process which is coming after that. Then we have to put another process which is coming after that. Then we have to put another process which is coming after that. So what CPU scheduler will do, because if it is using this particular algorithm, first come first serve, that is called FCFS scheduling algorithm. So that scheduling algorithm will always pick what is in the front of the queue. So it will pick up the front of the queue, because this particular process is in the front of the queue. So that process will be taken into the CPU, complete its process, go to the terminate state. Then again, CPU scheduler will pick who is in the front, because we have just deleted it from the front. So front will be pointing to this P2. So P2 will be coming here in the CPU. Execute its all instruction, terminate. Then P3 will come, execute its all instruction, terminate. Then P4 will come, execute its all execute its all instruction and terminate. So that is a very simple scheduling algorithm, which is called first come first serve scheduling algorithm. For this scheduling algorithm, we'll use the queue that is a simple queue that we have to use, and we have to put the process according to their arrival time, and based on that, the scheduling will be applied to each process. Whoever the process which is in the front will be allocating the CPU and will execute its all burst time, and it will be terminated. So what we have understood that in the first come first serve, so what is the criteria? Criteria is arrival time. So based on that criteria, we'll put the process into the CPU. The second thing is, what is the mode of this particular scheduling algorithm? So we have seen two type of mode, preemptive and non-preemptive. This particular scheduling algorithm is non-preemptive. What is the meaning of non-preemptive? Means once the process will be allocated the CPU, it will execute its all instruction, and then it will go to the terminate state. Means there is no line, there will be no line from, let's say this is ready, running, terminate. So if process is coming from ready to running, so from running it will go to the terminate. This is the transition. So there is no transition from running to ready. This transition is not there in the first come first serve algorithm. Let's see one example related to first come first serve algorithm. So we have three processes here, process 1, process 2, process 3. We have the related burst time which is written here. First burst time is 24. Second, for P2 burst time is 3. For P3 burst time is 3. What do you mean by burst time? Burst time means these are the time unit that is required to execute any of the process. So here process 1 is required 24 unit of time. Process 2 required 3 unit of time. Again process 3 required 3 unit of time. And what is the order of this? So the order is, what should be the order? The order will be like this. P1 is coming first, so P1 will go to the queue. Then P2 is coming, then P2 will come into the queue, and then P3 is coming, then P3 will be coming to the queue, right? So this is how we put the process into the CPU. Here we have another another attribute which are related to the process, which is called arrival time. So the arrival time will also be there. Let's say the arrival time of the process is 0 millisecond. The arrival time of process 2 is 1 millisecond. The arrival time of process 3 is 2 millisecond. It means in 0. So these are all relative timing. Okay. It is not the, let's say 10 o'clock or 12 o'clock. It is not like that. These are all relative time. So for a particular starting time, let's say the starting time is 10 o'clock, 10 a.m. That particular starting time, P1 is there. And after 1 millisecond, P2 came. And after 1 millisecond, P3 came. That's why the arrival time is 0. This is 1 and this is 2. So 1, 2, 3 is not a time. It is a relative time. So in that way, the queue has been arranged, and we know that the queue is deleting the data from the front and putting the data into the rear side. So if another process will come, it will come to the rear side. This is my front. So P1 will be execute first. So it will take 24 unit of time. Then P2 will be coming after that. Then it will take 3 more unit of time. So it will be 27 total. Then P3 will come. It will again take 3 unit of time. So it will be 30. This particular chart, which is written, which is drawn here, it is called Gantt chart. That will tell me that how much time they have spent into the CPU. This Gantt chart will tell me that process 1 is there in a relative time from 0 to 24 unit of time it has spent into the CPU. Then after that, which will come? P2 will come because it is the second one here. Then P2 will spend 3 unit of time. So from 24 plus 3, 27, it will execute into the CPU. Then P3 will come. So P3 will come after that. Then 27 plus 3, 30. So 30 unit, up to 30 unit of time, P3 will going to be there into the CPU for execution. So what is the completion time here? So the completion time which is written here is this is 30 unit of time. So 30 unit of time is your completion time. Okay. So here in this particular chart, what is the completion time of P3? So I'll write here. Process. Let's say we have arrival time and we have burst time, which is given, right? So we have process P1, P2, P3. Arrival time is, let's say 0, 1, and 2. In that way, we are making the queue. The burst time is here 24. This is 3, and this is also 3. So here, if you'll understand what are the different time or duration we have related to the process. So the first time or duration is completion time. So let's calculate the completion time of T1. So what is the completion time of P1? Completion time of P1 is 24. So at 24 of time, 24 unit of time, that has been completed. Which one? Process P1 has been completed. Now P2 has completed at 27 unit of time. and P3 has completed as 30th unit of time. So I think completion time is finished. Now the next is turnaround time. What is turnaround time? We know the formula of turnaround time. So the formula of the turnaround time is completion time minus arrival time. Right? So what is the completion time? Completion time is 24. What is the arrival time is 0. So what is the turnaround time here is 24. Now completion time of P2 is 27. 27 minus arrival time is 1. That is called 26. Then completion time of T3 is 30 and it has been arrived at 2. So the turnaround time is 28. This is how we'll calculate turnaround time related to every process. Now come to another time duration, which is called waiting time. So what is the waiting time of process P1? So waiting time will be like how much time this process has spent into the ready queue. So the formula for waiting time is how much time it has been spent into the ready queue. That is waiting time. But there is a formula is turnaround time minus burst time. That is a formula for waiting time. So what is waiting time? Turnaround time minus burst time. So what is the turnaround time is 24. What is the burst time is 24. So what is the waiting time? 0. So 0 unit of time it has been spent into the ready queue. Which one? P1. Because once P1 has arrived, at that particular time it has been allocated the CPU. Getting it? That's why the CPU is starting from 0 and ending at 24 because 24 is the burst time for P1. Let's go for P2. What is the turnaround time is 26. What is the burst time is 3. So how much time it has spent into the ready queue? It is 23 unit of time. Process 2 has been waiting into the ready queue. Now come to the third one, which is turnaround time is 24 and the burst time is 3. So how much it is? It is 25 unit of time. This P3 has been spent into the ready queue. So I think you all get all this timing. So in the examination, you have been given the process, you have been given the arrival time, you have been given the burst time. What you have to calculate? You have to calculate the completion time, you have to calculate the turnaround time, and you have to calculate the waiting time. And at last, what you have to find it out? You have to find it out average turnaround time and average waiting time. So how you'll calculate average turnaround time? It is add all these turnaround time means 24 plus 26 plus 28 and we'll divide it by 3 because we have 3 processes. Likewise, for the waiting time, we will add all the waiting time, that is 0, 23 and 25 and we'll divide it by 3. So that is your average waiting time and this is average turnaround time. Another thing that we have to talk about related to first come first serve scheduling is the queue arrangement. So the first criteria is arrival time, right, for the queue. So queue will be, the queue of the process will be arranged based on the arrival time. But if the arrival time is the same, so we have to pick up the process ID. And based on the process ID, we have to make sure that which will come first and which will come after that. So as we can understand from here is, this process has process ID 1, this process has process ID 2, this process has process ID 3. Even though they have arrived at 0, 0, 0, we have to arrange the queue based on their process ID. This is the tiebreaker for it. Otherwise, we have to take this particular criteria, that is arrival time. If arrival time is same, we have to consider process ID. Getting it? For the arrangement of the queue. That is one thing.